Managing complexity, part 2. So we now know that we have to form subproblems to solve a problem. There are many ways to break down a problem into subproblems. What is then a good way or good ways to see it? In this part of managing complexity, we see some general guidelines on doing that. Hopefully, all this can help you in coming up with a solution that is easy to understand to yourself and to others who need to read your codes. On the whole, the more programs you work on, the better you become in knowing what is really good abstraction. Here's the list of consideration we have to do good abstraction. We'll go through them in detail next. At the very last slide of this video, we will summarize all this in a few keywords to be remembered when solving a computational problem. 1. Make it more natural to think about subtasks. A house is made up of bricks and other building material. But to think of a house as a bricks, this is not quite natural. Instead, you can think of house as many rooms, and rooms make up of bricks. In the same way, a program is made up of primitives, but if you think of a program as primitives only, then you will have a big program consists of just primitives. Instead, you should organize your programs as functions, and functions make up of primitives. This way of thinking is more natural because we now have functions with proper names to make clear what they are at different parts of the program, rather than a bunch of primitives with no obvious meaning. This is also related to the next point. 2. Make programs easier to understand. You have seen this code before in top-down approach to write hypotenuse as 3 functions. Why don't we just combine all this into one simple line, return square root a star a plus b star b. Yes and no. Yes, that this one line is rather concise and clear and for this particular problem. But no, in that we no longer know that this is from the Pythagoras theorem. I agree that this is too simple a case to push this point to you, but you should understand our purpose of illustration here. What about this next version? We'll put back the square x as a private function within hypotenuse. So this private function is not visible to other functions outside our hypotenuse. And we return square root of square a plus square b. So nothing wrong in this case, it seems cool, nested. But is this really better? This is debatable too. I shall leave this to you to consider the issue about having a private function square within hypotenuse. 3. Good abstraction is to capture common patterns. For example, you have seen this in lecture 2, stacking R cross BB 4 times in certain manner. This is to form a cross. And this particular routine, besides applying to R cross BB, it could be used for COBB, etc. So we could abstract it out as giving it a name, define, make cross, picture, and change all these references to R cross BB to become picture. And this is now a general routine that you can make cross for many other pictures. This is also related to the next point. 4. Good abstraction is to allow for code reuse. For example, you have seen the square function is used in sum of squares, and actually square can also be used in calculating area of circle. Area of circle, given its radius, is simply pi times square r. Likewise, if you want area from diameter, you can do circle area from radius, the diameter given divided by 2, and reuse this code. So in this case, it's good that you abstract out square as a separate function so that it could be used for circle area from radius as well, besides the sum of squares. 5. Good abstraction is to hide irrelevant details from the user, as in other subjects such as chemistry, where water molecule is represented as H2O. This is good enough for some chemical analysis and it serves its purpose. Same for us. You have seen stereogram generator as presented by Ben Leong, but you have no idea how these work. You only know that it takes in the depth map and it produces the required stereogram. So the detail about the stereogram generator is hidden from you. 6. Separate specification from implementation. This is related to the previous point. Hide irrelevant details. Specification of what for the car is, it allows one to drive it, and how does it work to allow one to drive it. Take a look at the programming example. Define square of x is return x star x. So square x is defined in this particular way. When you put square 2, you get 4. Put square 3, you get 9. Well, you can do it in another way. Define square x is return exponent 2 times log of x. When you put square 2, you get 4.0 instead of 4. So this is the same. Square of 3, now you get 9 point something. In this case, this implementation is better than this implementation. So we only know from outside square x is to get the square of some number. That is the what part. As to the implementation part, is either this x star x or this exponent of log. So this is an illustration of two different ways of implementing square x. Now, in programming, at time, we need to have all these different ways of implementing the same abstraction. As to why this is so, you will learn that we need to be able to do this so that we can experiment with different approaches for purposes like efficiency. 7. A good abstraction can make debugging easier. So for example, define hypotenuse A, B is written in this manner. This is not obvious that what is the problem. On the other hand, if you have written it in this manner, it is easier to see that the error is because of the square x is written as x plus x instead of x star x. So this is a simple illustration. You should imagine that at time, by writing something more explicit with a name allows you to have a quicker comprehension of what you actually written down. And that could possibly help in debugging. In fact, you will be spending a lot of time on debugging. Often it is advisable that you have to invest a bit of your abstraction to write codes that allows you to debug easier. Just to sum up at this point, 1. Abstraction is a way to help to hack information that are not really relevant. And 2. Abstraction should be done such that it avoids coupling. Avoid coupling meaning that for two different abstractions, their dependency should be kept to the minimum so that in changing one abstraction will not affect many other abstractions. Within an abstraction, everything about the abstraction is quite coherent. In one way, it means that the abstraction is doing one single task, and that helps to manage complexity better. Next is top-down design with wishful thinking. We did this in part 1. So all these are actually design principles in object-oriented design. It applies not just to Python, but other languages like Java, etc. So bear in mind, information hiding, avoid coupling, and with top-down thinking, that helps you to design your solutions for a problem.